All right, so you're ready to tackle some serious physics. Want to really get a grip on these fundamental ideas without needing, years of study.
Well, you've come to the right place. Today, we're going deep, really deep into Einstein's theory of relativity. And yes, we're going to take on that famous E = mc years equation.
We've got some awesome explanations lined up for you, and our goal is pretty simple. Pull out those core insights, the mind-blowing stuff, and see why they matter so much.
Yeah, we're cutting through the noise to get right to the heart of it. No detours.
So think about this. Before Einstein came along, people just kind of assumed space was space and time was time. It was all very fixed and absolute, right? Everyone experienced it the same way.
Pretty much, yeah.
Then, boom, along comes Einstein, this brilliant, revolutionary physicist.
Yeah, he kind of just blew everyone's minds. He was all like, nope, that's not how it works.
He challenged some seriously fundamental beliefs about the universe.
And he didn't just pull these ideas out of thin air. He was building on the work of other physicists, just pushing those boundaries,
And what he gave us was really two big pieces of this puzzle. First, in 1905, we got special relativity, which looks at what happens when things are moving super fast.
Super, super fast, like close to the speed of light, kind of fast.
Right. And then about 10 years later, he gives us general relativity, which tackles gravity and this crazy concept called space-time. It's like this four-dimensional fabric of the universe. It combines those three dimensions of space with the dimension of time.
Yeah, space and time are so intertwined, it's hard to wrap your head around sometimes. But general relativity gives us a much more complete picture.
Absolutely. So let's start with special relativity, and this is where E if CR really comes into play. One of the big things here is the idea that there's a universal speed limit.
It's a cosmic speed bump.
Yeah. And that limit is the speed of light. Nothing can travel faster than that.
What's so fascinating about this is how it affects our entire understanding of reality. We kind of take it for granted that space and time are these fixed things. But at these incredible speeds, our everyday intuition just doesn't hold up.
Which brings us to another mind-bending idea, time dilation.
Right, so picture this. You're cruising around in a spaceship going at, I don't know, say 90% the speed of light.
Okay, I'm in the spaceship.
So for you, inside the spaceship, time would actually pass a little bit slower compared to someone back on Earth.
Really? Time itself slows down.
Yep, it's like, imagine a pair of twins, right? One blasts off into space at this crazy speed, and the other stays on Earth. When the space twin comes back, they'll actually be a bit younger than their Earthbound twin.
Whoa, so it's not just a theory. This actually happens.
It does. They've actually measured this effect in experiments, even with super accurate clocks on airplanes.
Wild. Okay, now for that famous equation. E = mc = b. It looks simple enough, but it's packing some serious power.
Yeah, it's deceptively simple.
So E stands for energy, M is for mass, which is basically the amount of matter in something.
Right, how much stuff it's made of.
And then c = b is the speed of light squared, which is, well, it's an incredibly huge number.
Massive. The key here is that mass and energy aren't these separate things. They're fundamentally the same, just in different forms.
So E = mc is telling us how much energy is locked up inside even a tiny bit of mass.
And think about it. It's not just about things like atomic bombs.
Right.
This same principle powers the sun. It converts a tiny, tiny fraction of its mass into all the light and heat that supports life on Earth.
It's a constant mind-blowing demonstration of this equivalence between mass and energy.
Totally.
Okay, so a tiny bit of mass can become a massive amount of energy. And the classic example, of course, is the atomic bomb. That's EECM and COA in action. A small amount of uranium is converted into this massive explosion.
It's a stark example of the incredible power contained within matter.
For sure. Okay, let's switch gears a bit and talk about general relativity. This is where Einstein completely revolutionized our understanding of gravity.
Yeah, before Einstein, gravity was this force that pulled objects together. That's what Newton told us.
Right, like the Earth pulling down on us.
Exactly. But Einstein said, hold up, it's not a force. It's all about the bending of space-time. Massive objects like planets and stars actually warp the fabric of space-time around them.
Okay, so try to picture this. Imagine a bowling ball on a trampoline. The bowling ball creates a dip in the fabric, right?
Yeah, that's a pretty good analogy. The dip represents the curvature of space-time caused by the bowling ball, which in this case is like a planet or a star.
Remember, space-time is four-dimensional. It's not just like a flat trampoline, so the curvature is much more complex.
For sure. but the analogy helps to visualize it.
Totally. So this curvature is what we experience as gravity. When the Earth orbits the sun, it's not being pulled in by some invisible force. It's following the curves in this giant space-time bowl created by the sun's mass.
It's like it's rolling around in a cosmic dip.
Exactly. So to kind of recap what we've learned from our sources, special relativity shows us that time and space aren't fixed. They change with speed. And expel MC Doa tells us that a small amount of mass contains a crazy amount of energy. General relativity reveals that gravity isn't a force, but the curvature of space-time caused by massive objects.
It's pretty amazing, isn't it? Like, just how much our understanding of the universe has changed thanks to Einstein.
It's completely mind-blowing. He showed us that space and time are way more dynamic and interconnected than we ever realized, and the relationship between mass and energy is incredibly deep. Gravity isn't a pull, it's a warp in the fabric of reality.
It makes you wonder what else we might discover, right? Like, what other seemingly fixed concepts could be way more fluid than we understand?
It's a great question to consider. So, going back to that space-time bowl analogy, if gravity, this fundamental force, is actually the curvature of space-time, influencing the paths of everything, even light itself, what does that tell us about other things we think of as fixed or absolute? Could they also be more interconnected than we currently realize?
It's definitely something to think about, just to ponder. Maybe our understanding of the universe is just scratching the surface.
Maybe we're just at the beginning.
Exactly.
Thanks for joining us for this deep dive. We'll see you next time.
See ya.